welcome to this problem walkthrough. Today, we'll explore the problem number 1237, find positive integer solution for a given equation. In this session, we'll discuss the problem statement, dive into various approaches to solve it, and analyze their complexities. Let's dive in. In this problem, you are given a function f, x, y, that returns a positive integer. This function has two key properties. It is monotonically increasing with respect to both x and y. This means that as x increases, the value of f, x, y also increases, and as y increases, the value of f, x, y increases as well. The function is provided through a predefined class called custom function, and it can be called using custom function.f, x, y. Your goal is to find all pairs of positive integers, x, y, such that the value of the function equals a given target z. The input consists of the custom function object and the target integer z, where z lies between 1 and 10,000. The output should be a list of all pairs, x, y, that satisfy the equation f, x, y equals z. These pairs can be returned in any order. To understand this better, let's look at an example where the target value z is 5, and suppose the function f, x, y is defined as x plus y. Since the function satisfies the monotonicity conditions, we can determine all pairs, x, y, such that x plus y equals 5. The possible pairs are 1, 4, 2, 3, 3, 2, and 4, 1. These pairs, when added together, all result in the value 5. The output for this example is a list of these pairs, which can appear in any order. This demonstrates how the function's monotonicity helps narrow down the possible solutions and ensures that the pairs are positive integers. Now, consider another example where the target value z is 8, and the function f, x, y is again defined as x plus y. Here, we need to find all pairs, x, y, such that their sum equals 8. The valid pairs for this case are 1, 7, 2, 6, 3, 5, 4, 4, 5, 3, 6, 2, and 7, 1. Each of these pairs satisfies the equation x plus y equals 8, and all values are positive integers. The output is a list of these pairs, which, as before, can be returned in any order. This example further highlights how the function's monotonicity allows us to systematically find all possible solutions. There are a few important constraints to keep in mind for this problem. The values of x and y must both be between 1 and 1000, and the target value z lies between 1 and 10,000. Additionally, the function f, x, y is guaranteed to be monotonically increasing with respect to both x and y. This property ensures that the search space for solutions is manageable. When considering edge cases, if the target z is very small, such as 1, the only possible pair is 1, 1. On the other hand, if z is large but no pairs satisfy the equation, the output should be an empty list. Finally, if the function grows steeply, the number of valid pairs may be limited. These constraints and edge cases are crucial for designing an efficient solution to the problem. To solve this problem, we first considered the brute force approach, which is the most straightforward method. The idea is to iterate through all possible values of x and y, starting from 1, and evaluate the function f, x, y for every pair. If the result matches the target value z, we count that pair as a solution. In practice, this involves looping x from 1 up to a large upper bound and, for each x, iterating y from 1 onwards until the function value exceeds z. At that point, we can stop the inner loop early to avoid unnecessary computations since the function values only increase further. While this approach is simple and easy to implement, its computational complexity is m*n, where m and n represent the ranges of x and y. This makes it impractical for large inputs due to the significant number of redundant calculations. Importantly, this inefficiency arises despite the monotonicity of the function, which the brute force method doesn't take advantage of effectively. Now, an alternative and more efficient method is the two-pointer approach, which leverages the monotonic nature of the function. The key intuition here is that instead of testing every possible combination of x and y, we can strategically navigate the search space using pointers. We start by setting x to 1 and y to a high value. By evaluating f, x, y, we observe how the function behaves. If the value is less than z, we increase x to make the function larger. On the other hand, if the value exceeds z, we decrease y to make the function smaller. If we find that f, x, y equals z, we record the pair as a valid solution and adjust the pointers to explore further possibilities. This process continues until x exceeds the upper limit or y drops below 1. The result is a significant reduction in unnecessary evaluations, giving this approach a complexity of O(m plus n). This method is particularly effective because it fully exploits the monotonicity of the function, making it both faster and more elegant than brute force. Another option we considered is the binary search approach, which also takes advantage of the function's monotonicity. Here, the idea is to fix x and use binary search to quickly find a suitable value of y such that f, x, y matches z. For each x within the feasible range, we perform a binary search on y. If we find a match, we record the solution. The complexity of this method is O(m log n), where m is the range of x and n is the range of y, making it more efficient than brute force. However, there are trade-offs. While binary search is competitive in terms of performance, it introduces additional coding complexity due to the need for careful implementation of the search logic. Moreover, it's less intuitive compared to the two-pointer approach, which achieves similar efficiency with a simpler and more direct strategy. For these reasons, we opted not to use the binary search approach for this problem. Ultimately, we chose the two-pointer approach as the most suitable solution for this problem. The key observations that led to this decision include the monotonicity of the function, which allows us to prune the search space effectively. By incrementing x to increase the function value and decrementing y to decrease it, we can systematically traverse the solution space without redundant checks. This efficiency is a sharp contrast to the brute force method, which doesn't leverage the function's properties. The turning point was recognizing how well this approach aligns with the problem's constraints, providing an optimal balance between simplicity and performance. While binary search is also efficient, the two-pointer strategy stands out for its straightforward implementation. With a complexity of O(m plus n), this method is both practical and elegant, making it the ideal choice for finding positive integer solutions to the given equation. To solve the problem of finding positive integer solutions for a given equation, we can start by exploring a brute force approach. This method systematically examines all possible pairs of integers, x and y, to identify those that satisfy the equation f, x, y equals z. The first step is initialization. Here, we define the function f, x, y, based on the specific problem requirements. For example, it might involve operations like x squared plus y squared or x multiplied by y. We also decide on a target value z, which is the value we want the function f, x, y to equal. Additionally, we set an upper bound, n, for the values of x and y. This bound is crucial because it ensures our search is exhaustive yet computationally feasible. With these elements in place, we can begin iterating over the values of x. Now, for the iteration process, we start with x ranging from 1 to the upper bound n. For each value of x, we initiate a nested loop for y, also ranging from 1 to n. Within this inner loop, we compute the value of f, x, y, for the current pair of x and y. Once we have this computed value, we check whether it matches the target value z. If the condition f, x, y equals z is satisfied, we record the pair x, y as a valid solution. These solutions can be stored in a list, a set, or another appropriate data structure depending on the problem's requirements. After completing all iterations over x and y, the final step is to return or output the list of all valid pairs that satisfy the equation. This brute force method works by exhaustively checking all combinations of x and y, ensuring that no potential solution is missed. Although simple, it guarantees correctness as long as the upper bound n is sufficiently large. However, there are ways to optimize this approach. For instance, if the function f, x, y is symmetric, such as x squared plus y squared, we can reduce the search space by only considering pairs where x is less than or equal to y. This avoids duplicate solutions and improves efficiency. Another optimization is early termination. If the computed value of f, x, y exceeds the target z, we can break out of the inner loop for that specific x, as further increasing y will only lead to larger values. Precomputation is another helpful technique, especially for functions involving repeated calculations like powers or factorials. By precomputing these values once, we can save significant computation time during the iterations. Finally, the choice of data structure can also impact performance. Using a list is ideal if the order of solutions matters, while a set is better if we need unique solutions without caring about order. For small ranges of x and y, a 2D array can even be used to directly map which pairs are valid solutions. When analyzing the complexity of this brute force approach, the time complexity is O(n squared). This is because the algorithm examines all combinations of x and y within the range of 1 to n, and there are n squared such pairs. The space complexity, on the other hand, is O(k), where k represents the number of valid solutions stored in memory. Let's consider an example to see the algorithm in action. Suppose f, x, y equals x squared plus y squared, the target value z is 25, and the upper bound n is 10. Starting with x equal to 1, we iterate over y values from 1 to 10. For y equal to 4, the equation 1 squared plus 4 squared equals 25 is satisfied, so we record the solution, 1, 4. For y equal to 5, the result exceeds 25, so we break the inner loop. We then repeat this process for x values 2, 3, and so on, recording solutions like 3, 4, and 4, 3. Finally, we output all valid pairs, ensuring that every solution is found. This example highlights how the algorithm systematically explores the solution space while employing optimizations like early termination to improve efficiency. This solution uses a two-pointer approach to efficiently find all pairs, x, y, such that the given function f, x, y, equals the target value z. The function f, x, y, is provided via the custom function object, and we assume it is monotonically increasing in both x and y. The algorithm starts with x initialized to 1, the smallest positive integer, and y initialized to 1000, the upper bound for positive integers per the problem constraints. The main idea is to iteratively adjust the values of x and y based on the result of f, x, y. If f, x, y equals z, the pair x, y is added to the result list, and the algorithm moves to the next possible pair by incrementing x and decrementing y. If f, x, y is less than z, x is increment to increase the value of f, x, y. Conversely, if f, x, y is greater than z, y is decrement to decrease the value of f, x, y. This ensures that we systematically explore all valid pairs without redundant computations. The use of two pointers ensures that the algorithm runs efficiently within the constraints, as it only performs a single pass through the possible values of x and y. The final result is a list of all pairs, x, y, that satisfy the equation. To solve this problem, we begin by defining the interface custom function, which represents the function f, x, y. This interface is provided by LeetCode, and its implementation will be handled during the actual testing of the solution. Our goal is to find all pairs of positive integers, x, y, such that f, x, y equals the target value z. In the solution class, we define a method findSolution which takes the custom function and the target value z as inputs. Inside this method, we initialize an empty list called result to store the valid pairs. We also initialize two pointers x starts at 1, representing the smallest value for x, and y starts at 1000, representing the largest possible value for y. This two-pointer approach ensures that we efficiently explore the solution space. Next, we enter a while loop that continues as long as x is less than or equal to 1000 and y is greater than or equal to 1. Inside the loop, we compute the value of f, x, y by calling the custom function .f method. Based on the result, we either add the pair to our result list, increment x, or decrement y to move closer to the target value z. The loop continues adjusting x and y based on the comparison between the computed value of f, x, y, and the target value z. If f, x, y is less than z, we increment x to increase the value returned by the function, since increasing x generally moves us closer to z. Conversely, if f, x, y is greater than z, we decrement y to decrease the value. When f, x, y equals z, we add the current pair, x, y, to the result list and then adjust both pointers, incrementing x and decrementing y, to explore other potential pairs. After the loop completes, we simply return the result list, which contains all the valid x, y pairs that satisfy the condition f, x, y equals z. This approach ensures that we efficiently search for solutions while avoiding redundant computations, leveraging the constraints of the problem to systematically narrow down the solution space. To solve this problem, we need to find all pairs of positive integers, x and y, such that the function f, x, y equals a target value z. The function f, x, y is monotonically increasing in both x and y. This property ensures that increasing x or y will not decrease the value of the function, which is useful for implementing an efficient strategy. The plan involves using a two-pointer approach. We start with x at its smallest possible value, which is 1, and y at its largest possible value, which is 1000. We then compute f, x, y, and compare it to z. If the result matches z, we record the pair and adjust both pointers incrementing x and decrementing y to continue the search. If the value is less than z, we increment x to increase the result, and if it's greater than z, we decrement y to reduce the result. This process continues until either x exceeds 1000 or y becomes less than 1, ensuring that we consider all valid pairs without unnecessary computations. Now, let's look at an example where f, x, y equals x plus y and the target z is 5. We start with x set to 1, y set to 1000, and an empty result list. Initially, we calculate f, 1000, which equals 1001. Since this is greater than 5, we decrement y to reduce the value of f, x, y. This process of decrementing y continues until y reaches 4, where f, 4 equals 5. At this point, we add the pair 1, 4 to the result list and update the pointers incrementing x to 2 and decrementing y to 3. We then compute f, 2, 3, which also equals 5, so we add 2, 3 to the result and adjust the pointers again. This pattern repeats for the pairs 3, 2, and 4, 1, which are added to the result as well. Finally, when y becomes less than 1, the process stops. The output for this example is the list of pairs 1, 4, 2, 3, 3, 2, 4, 1. In this example, the function f, x, y is x times y, and the target z is 6. We initialize x to 1, y to 1000, and the result list is empty. The first calculation, f, 1000 equals 1000, which is greater than 6, so we decrement y. This continues until y reaches 6, where f, 6 equals 6. We add the pair 1, 6 to the result and update the pointers. Next, we calculate f, 2, 5, which equals 10 greater than the target. Therefore, we decrement y to 4 and continue. When y reaches 3, f, 2, 3 equals 6, so we add 2, 3 to the result and adjust the pointers. Similarly, f, 3, 2 equals 6, and we add 3, 2 to the result. At this point, y decreases to 1, where f, 4, 1 equals 4, which is less than 6. Since further increments to x would only increase f, x, y, we stop. The output here is 1, 6, 2, 3, 3, 2. For this example, the function is x squared plus y squared, and the target z is 50. We start with x set to 1, y set to 1000, and an empty result list. The initial computation, f, 1000, results in a very large value, so we decrement y repeatedly. When y reaches 7, we find that f, 7 equals 50. We add 7 to the result and adjust the pointers. Next, with x increment to 2 and y at 6, f, 6 equals 40, which is less than 50. To increase the value, we increment x to 3. Here, f, 6 equals 45, so we increment x again to 4. When f, 6 exceeds 50 at 52, we decrement y to 5. This process continues, but no other pairs satisfy the condition before x exceeds 1000. The final output is 7. Here, we analyze the time complexity of our two-pointer approach. First, the outer loop uses a pointer x, which starts at 1 and increases to a maximum of 1000. This gives us up to 1000 iterations for the x pointer. Inside this loop, the y pointer starts at 1000 and decreases as needed. The key observation here is that y only moves in one direction, downward, throughout the process. This zigzag traversal ensures that the total number of movements by both pointers combined is at most equal to the size of the grid, which is 1000 by 1000. Additionally, we evaluate the function custom function.f, x, y once per iteration, and since the function is treated as a black box, its internal operations do not affect the big O analysis. Combining these observations, the total time complexity for the algorithm is O, m plus n, where m and n are the bounds for x and y. Given that both bounds are 1000 in our case, the complexity simplifies to O, 1000 plus 1000, which is O, 2000, or simply O, 1000, in big O notation. Now, let's examine the space complexity. The primary contributor to the space usage is the result list, which stores all valid pairs, x, y, where the condition f, x, y equals z is satisfied. In the worst-case scenario, if the function returns a valid pair for each possible grid cell, the result list would hold at most 1000 pairs. Beyond this, the algorithm only uses two pointer variables, x and y, which consume constant space. Additionally, the black box function custom function.f, x, y, does not require any extra memory for its operations. Therefore, the total space complexity of this solution is dominated by the size of the result list, which is O, k, where k represents the number of valid pairs. In the worst case, k could be as large as 1000, resulting in a space complexity of O, 1000. Let's now compare this optimized two-pointer approach with a brute force method. A brute force solution would involve iterating through all possible values of x and y, essentially evaluating the function f, x, y, for every combination within the grid. This results in a nested loop with a time complexity of O, m asterisk n, which for our grid size of 1000 by 1000 evaluates to a total of 1 million computations. In contrast, the two-pointer approach significantly reduces this to O, m plus n, making it far more efficient. Examining the best, average, and worst-case scenarios, in the best case, the solution is found early, requiring fewer iterations, which makes the complexity close to O, m. On average, the pointers traverse a large portion of the grid, leading to O, m plus n. In the worst case, the pointers cover the entire grid, such as when no solutions exist or z corresponds to the maximum value of f, x, y, still maintaining O, m plus n. Mathematically, this is optimal because each grid cell is evaluated at most once, resulting in a linear relationship with the grid's perimeter. This is a stark improvement over the brute force O, m asterisk n approach, which redundantly evaluates every cell. When working on this type of problem, several common mistakes often trip up candidates. First, ignoring edge cases can be detrimental. While the problem description might emphasize positive integers, variations could include 0, negative numbers, or very large ranges. Failing to account for these can lead to solutions that break down during testing. Next, brute force approaches, though a good starting point, should not be your final solution. Without optimizing, brute force can result in poor time complexity, often O, in superscript 2, or worse. Interviewers value your ability to refine these initial solutions. Another pitfall is not handling duplicates correctly. For instance, when finding unique pairs, neglecting to filter duplicates can produce incorrect results or inflate the count of valid solutions. Finally, overcomplicating your implementation is another issue. Introducing unnecessary data structures or overly complex logic can make your solution harder to debug and explain, especially within the time constraints of an interview. Even with correct logic, small errors like returning the wrong output format, such as tuples instead of lists or results in the wrong order, can lead to test case failures. These mistakes, while seemingly minor, can consume a lot of debugging time if overlooked. To excel in interviews, focus on optimization. Start with a straightforward brute force approach, but then demonstrate how you reduce the time complexity. Techniques like binary search or two-pointers can be particularly effective if the input is sorted. Recognizing patterns is also crucial. Problems involving pairs, sums, or products often share common strategies, such as hashing, sorting combined with two-pointer methods, or even mathematical techniques. Additionally, always communicate your trade-offs. For instance, you might explain that while a hash map reduces lookup time to O(1), it comes at the cost of additional space usage. Lastly, practice handling edge cases. Proactively considering scenarios like empty inputs, duplicates, or maximum input sizes can set you apart by showing thorough problem solving. Understanding related problems can help you identify transferable strategies. For example, the two-sum problem focuses on finding a pair that sums to a target value, while three-sum extends this to triplets and often involves sorting in two-pointer techniques. Similarly, for some generalizes this approach to quadruplets, emphasizing the need for optimization and careful edge case handling. The count of smaller numbers after self problem introduces another dimension, requiring pairwise comparisons and often leveraging advanced techniques like binary search or merge sort. Additionally, exploring alternative approaches can broaden your toolkit. Assorting combined with a two-pointer method is highly efficient for problems involving sums or products. Sorting pre-processes the data in O and log n, while two pointers reduce the search space to O, n. However, this comes with the trade-off that sorting modifies the input and requires extra pre-processing time. On the other hand, hash maps allow for quick lookups, typically in O(1), making them ideal for problems needing frequent access to previously seen values. The trade-off here is increased space complexity, and in rare cases, hash collisions could occur. Binary search is another powerful technique, especially when the input is sorted or can be sorted. It reduces the search complexity to O log n per query, which is highly efficient. However, it does require the data to be sorted beforehand, and implementing binary search correctly can be tricky for beginners due to its inherent edge case sensitivity. For problems that require exhaustive searches, recursive backtracking is a useful approach. It's particularly effective for generating combinations, subsets, or other exhaustive solutions. The primary trade-off with backtracking is its exponential time complexity in the worst case, making it more suitable for small input sizes. Balancing these techniques based on the problem's constraints and requirements will help you craft robust and efficient solutions. Thank you for staying with us until the end. Today, we've walked through the find positive integer solution for a given equation problem. We've covered the brute force approach, discussed its strengths and limitations, and highlighted key insights for solving similar problems. Don't forget to like, subscribe, and keep practicing. See you in the next problem walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!